Hello, everyone. I'm Jiyang. I'm very glad to have this opportunity to, on behalf of Momenta, to give this presentation on the workshop of autonomous driving at CVPR 2023. Today, we are going to talk about how data-driven Flywheel enables scalable path to full autonomy. First, let me take about 1 minute to introduce Momenta. From day one to the future, Momenta's goal is always to achieve the scalable level 4, which means every car on the road with full autonomy capability, anytime, anywhere. And to achieve this target, the full autonomous driving product needs to be at least 10 times safer than the human drivers. To reach this goal, we need to solve millions of long-tail problems for autonomous driving. We found that we need at least 100 billion kilometers of driving data to solve all the long-tail problem and to validate the solution. To achieve this, we have two important insights. The first insight is that we cannot solve the long-tail problem by rule-based system, because we may solve hundreds of problems by hundreds of people, but we cannot solve millions of problems by millions of people. So we need a data-driven approach, and we also need a data-driven flywheel to automatically solve the millions of long-tail problems. That's our first insight. Our second insight is that we cannot achieve level 4 by just hundreds of cars or even 1,000 cars. We believe that the only path to achieve level 4 is to start the mass production by applying the software to the million of mass-produced cars and smartly collect data from these cars. That's the only way to collect enough data. These two important insights come up with our data-driven flywheel strategy. Momenta's flywheel has three important pillars. The first pillar is data-driven software. The second pillar is mass production data, which is collected from our mass production vehicles. And the third pillar is our closed-loop automation toolchain, which smartly filters, processes data, and trains our algorithms. Today, we have already accumulated 150 PB historical data, and our algorithm iteration is supported by multiple automakers' mass production vehicles. Okay, let's get back to the technical part. Today, we are going to share Momenta's Mapless solution. You can see that in this figure, we show that the system architecture. And there are three key important components in this architecture. The first one is perception. The second one is localization. The third one is planner. You can see that there is no HD map inside this, but we do have SD map and SD root. That SD means the standard definition. It's not high definition. We can see that the perception takes the SD map, multicam, and as input. LiDAR and radar here are optional, and it outputs the object and local map. The localization part takes the IMU, wheel speed, and GNSS, probably with RTK signal as input, and output the eagle pose in boot frame. Note that we still need a rough global eagle pose to align with our SD root. Together with the SD root object and local map and the eagle pose, these are sent into the planner. And inside the planner, we get the decision and the trajectory. And in today's sharing, we are going to introduce three key algorithms inside this architecture. In the perception part, we'll talk about the so-called DDLD, Data-Driven Landmark Detection algorithm. It produced our local map. And in the localization part, we're going to talk about the DDPF, Data-Driven Post-Fusion. Instead of using a common filter, we use a data-driven machine learning approach. And in the planner, we'll talk about how we use deep learning to solve the planning problem. Okay, let's start from the DDLD, Data-Driven Landmark Detection. The landmark detection task takes the multi-frame, multi-cam video as input and outputs the lane center lines, the lane boundaries, and the road boundaries. It also outputs some other elements like stop lines, crosswalks, and some other road marks. So basically, it generates the local map. It generates a local HD map from the perception. And we find that this is a quite challenging task. First, we face a diverse lane types. And in some scenarios, we have very complex road and lane geometry topology. Sometimes we have hard samples caused by occlusion, bad weather conditions, low light shadows, and some rain reflections. And sometimes we have the dynamic environment. So with all those challenges, we come up with a model architecture. It's a mixed ConvNet and transformer architecture. So basically, the image are processed by a ConvNet first, by some ConvNet, because we have multiple images as input. And all these features, encoded features, are processed by a transformer decoder, multiple transformer decoder layer. Different type of queries are input to the transformer decoder, and we have multiple type of outputs from that. So that's the basic architecture. We find that the ground truth generation is very important. The basic process is first we get a new trip data, and the new trip data can be from the road test or the production cars. It contains multi-camera videos or with high quality trajectory and some semantic point cloud. And first, we want to check whether this trip is covered by our existing DDLD map. If yes, then we have a relocalization with a map and have a new trip label. If no, then we need to collect multiple trips on this area, and then for each of them, we try to reconstruct the map. And then we align all the maps, all the map from the different trips together to have a higher quality map. And then we add it to the map database. Yeah, here is a video to illustrate how we generate the ground truth. You can see first we have the real-time mapping, and then we'll do the reconstruction. That's a first pass, single pass mapping. We have multiple passes, and then these passes are aligned together. So basically, we do the similar thing in urban and highway. Here is a constructed result. Okay, time is limited. We probably don't have enough time to watch all the video. So that's basically how we generate the ground truth. And here is a result from the DDLD. On the left is the image. On the right is the reconstructed is the detected landmarks. We have 3 types of landmarks shown here: lane center, lane boundary, and road boundary. Okay. First one is a highway. It's a sunny day and at night. Highway at night. And here is like a merging point in a rainy day. The current perception range is around 150 meters. Yeah, here you can see that's a very dark night, and at a very curvy road. The reason we limit the output to 150 meters is partially because of the computational resources. Here is a splitting point in a rainy day. Another merging point you can see here. That's a merging point in a sunny day. So next, we are going to talk about our deep learning planning. So first, we think the planning is a joint time-space search problem in a high-dimensional action space. To solve this problem, traditionally we use the like some optimization-based method or search-based method. We can always find that those kinds of methods cannot solve all the problems, so that's why we need a new solution. And we believe that the deep learning algorithm is a more efficient and more effective solution. So that's how we formulate the problem. The input includes the route information, that's a global route. And we also need the Eagle car info, like the history trajectory, and also the user setting. The user setting here is like the cruising speed, because in some scenarios, the driver wants to set the cruising speed, and we need to respond to this kind of input. And we also have the traffic light, static landmark, and dynamic object. Those three types of things are the environment. And note that the static landmark can be from the HD map or can be from the DDLD. That's the online perception. And the output, we have the multi-trajectories and the decision score on each trajectory. Here is the model architecture. It's basically a transformer-based model. Both the encoder and decoder are transformers. You can see that on the decoder part, we have two types of queries. The first one is Go query, and the second one is the object decision query. These two different queries can help us to generate multimodal trajectories. Okay, here, data production again. We find that the DLP is, the data quality is really important, really matters for DLP. We face different data issues in our engineering process, like the imbalanced data, the data distribution drift in the closed loop. And this problem is probably very different from the perception, because perception is not a closed loop, and planning is a closed loop. The output from the last frame can affect the input of the next frame. So that the distribution drift is quite a critical problem. And sometimes we have conflicted data, and in some scenarios, we don't have enough data. So to tackle those problems, we have different type of data generation pipeline. Here we'll list some of them, like fine-grained mining data pipeline, bad data filtering pipeline, and we'll also use a simulation to generate some of the data. We won't have enough time to go into the details, but here we just want to mention that data generation and data collection is very, very important for deep learning planning to work. We probably spend 80%, 90% of our time on the data issues. Okay, let's see result comparison on the cutting scenarios. So we have two types of metrics. The first one is safety metric. Second one is comfort metric, and we'll count the count per disengagement. So basically, how many times we have a disengagement on those cases. And we have three data set, cutting data set, truck trailer cutting data set, and the false positive break data set. Okay. So here you can see that compare with the traditional rule-based planning, the DLP basically achieve better performance on all dataset, on all metrics. On the cutting dataset, truck and trailer cutting dataset. The differences between these two is truck trailer cutting dataset is a more focused dataset. It only contains large vehicles. We focus a lot on the large vehicles because it's more dangerous. It can cause more safety issues. Yeah. And on the false positive break dataset, you can see the DLP also performs better than the traditional rule-based planning. So we can see that overall, DLP is much safer and more comfortable than traditional rule-based planning. Here are two examples. Okay, so this is first. On the left, we show the rule-based result, and on the right, we show the DLP result. Okay, you can see that here is a very slow vehicle cutting. And at this point, the DLP realized this scenario, we need to slow down, so it starts to brake. But the traditional method doesn't have this reaction. Yeah, the reaction comes slower. So that's why the DLP, it can show how DLP performs safer. Okay, so that's another example. On the right side, we have a large vehicle cut-in. You can see at this point, actually at this point, the DLP starts to brake, but the traditional method doesn't realize this. And that's another case that our DLP is a safer have a safer response. Okay, so next we are going to talk about the data-driven post-fusion. Data-driven post-fusion takes the IMU, the wheel pulses, steering angle, and the motor speed as input, and it tries to output a local equal pulse. So this local equal pulse is in the boot frame. Okay. We find that this is a quite challenging problem because this algorithm takes a lot of raw sensor input. It's not like DLP, the planning or the perception. Planning perception basically doesn't take much more, doesn't take a lot of the raw sensor input, but the post-fusion algorithm takes a lot of the raw sensor, the IMU, the wheel speed, the steering angle. All those are the very low-level sensor data. And for those low-level sensor data, we always find that there are a lot of sensor noises, like random walk. And for the wheel speed sensor, it can fail to detect very low speed. Sometimes it claps to the integer number or just clap to 0. And for Momenta, we want to deploy our algorithm and systems onto different vehicles, different type of vehicles. And for different type of vehicles, different platforms, basically, they usually will have different sensor set. If we have a common filter-based algorithm, we always need to manually tune a lot of parameters for adaptation. And this is very time-consuming. And the result sometimes is not very good. So that's why we want to have this data-driven algorithm. The machine learning process is just like the manual tuning parameter process, but it is done by machines. So it can save a lot of engineering time. And that's why it is very important for massive production vehicles. Okay, the network architecture is quite straightforward. We don't use the transformer architecture because we only allocate a very small portion of the computational resource on board to this DDPF model. So we just use a basic multi-layer perceptron to solve the problem. We take the IMU, the wheel speed, the wheel angle signal as input after a few layers processing, and then we output the localization result. It contains the position and the attitude. And note that we need to dealing with the sensor bias. That's in another mechanism, which is not included in this in this graph. Okay, again, data. For the DDPF data generation, we use fully automatic ground truth generation process. For driving, like for driving scenario like highway or urban scenarios, we'll use a high precision instead post-processing trajectory as the ground truth. And for the parking scenario, usually we don't have the GNSS or RTK signal, so that's why we have a LiDAR-based odometry. And once we have the generated data, generated ground truth, we find that carefully tune the data distribution is very important, and the data distribution in the motion space is the most important. So here we show two figures. On the left, the y-axis is a longitudinal velocity, and the x-axis is the angular velocity. On the left side, you can see that that's a traditional, that's the raw distribution. If we don't balance the data at all, then we will have a distribution like this. And on the right side is a distribution after we carefully tune the data. Yeah, and we found that this is very important. I will show some details later. We use the relative position error as the evaluation metrics. This is quite traditional. I don't want to spend much time on that, so let's just skip it. For the result comparison, we compare the DDPF, the data-driven post-fusion algorithm, with the traditional Kalman filter-based algorithm on both highway and parking test set. And you can see that DDPF outperforms the traditional Kalman filter-based approach with a 30% to 60% error reduction on all the scenarios. I think that's a quite significant improvement. And here is a comparison on the motion space. Right side is a DDPF, left side is the Kalman filter. You can see that basically on all the cells, the DDPF have a better performance. And in the process of model iteration, if we find some cell has a lower performance, then that's a very clear signal. Usually we will find fewer data on that cell. Then we just add more high quality data to that cell, and then we'll find a performance improvement. That's why I say that the motion space distribution balancing is very important. And that's a key point of how we make this work. Yes. Here is a video to show the comparison between the Kalman filter and the DDPF. Left is a Kalman filter, right is a DDPF. This is like a parking scenario. You can see that after this vehicle parked into this slot, you can see a small difference. Yeah, here you can see there's a small deviation, but on the right side is totally aligned. And this small deviation sometimes can cause a problem because for the parking scenario, 10 centimeters, 5 centimeters make a difference. We always have a very tight space there. So that's why we care about the local equal-pose accuracy. Okay, so I think that's all for the DDPF. Okay, let me take this slide as a summary for my presentation. In Momenta, we believe that the data-driven algorithms and the massive data are critical to scalable L4, and we are working very hard to realize the full data-driven algorithms. For now, as you can see, we are in generation 3. The DLP and DDPF have been deployed in mass production vehicles, the Cyc IM car, which is a very cool brand in China. And DDLD is about to deploy in Q3 this year. In the future, we'll have generation 4 and 5. This evolution is just like how the human brain works. We believe in the future, the autonomous driving system will finally develop into one big model, just like human brain, which is another interesting topic. Hopefully we can share this next time. Okay, thanks. That's all for my today's presentation.